You've been told a story about the universe's origin. It goes like this. In the beginning, there was nothing. Then, spontaneously, without cause or reason, the universe exploded into existence. Everything came from nothing through quantum fluctuations or random chance. It's a creation story for the scientific age. Materialist cosmology's answer to "let there be light," except it's not true. Not in the way it's been explained to you. The universe didn't come from nothing. It couldn't have. The very concept is incoherent, a misunderstanding of what physicists actually mean when they use words like nothing and vacuum and void. But this myth persists because it's convenient. It lets cosmologists avoid uncomfortable questions about what existed before the Big Bang, about ultimate origins, about whether the universe requires explanation beyond physics. It creates the illusion that science has answered the deepest question of existence, when actually it's redefined the question into something answerable. And many scientists know this. In technical papers and private conversations, they acknowledge that something from nothing is a misleading oversimplification. But in popular accounts, in science documentaries, in public lectures, the myth continues unchallenged because it's compelling, because it's easier than explaining the nuances, because it satisfies a deep human need for cosmic origins to make sense. If you're ready to learn that the universe's origin story is more complex and more mysterious than you've been told, subscribe and prepare yourself. What you're about to discover reveals how scientific language can obscure as much as it illuminates. We begin. The universe from nothing narrative became popular in the late 20th century as cosmologists developed models of cosmic origins that seemed to eliminate the need for any pre-existing conditions. Quantum cosmology suggested the universe could spontaneously nucleate from a quantum vacuum. Inflationary theory proposed that a tiny fluctuation could grow exponentially into the vast cosmos we observe. These theories were revolutionary and technically sophisticated, but when translated into popular language, they became oversimplified into claims that the universe literally came from nothing. No space, no time, no laws, no anything. Physicists like Lawrence Krauss wrote best-selling books arguing that physics now explains how something comes from nothing, that we don't need theology or philosophy to answer origin questions. The universe is a free lunch, a cosmic accident, requiring nothing beyond the laws of physics to explain. This narrative resonated. It appealed to those who wanted a purely naturalistic account of cosmic origins. It seemed to eliminate the need for a creator or first cause. It positioned science as capable of answering questions that were once purely philosophical or religious. But the narrative rests on a deception, perhaps unintentional, but deceptive nonetheless. When physicists say nothing, they don't mean what ordinary people mean. They mean quantum vacuum, which is decidedly not nothing in the philosophical sense. The quantum vacuum is a state of lowest energy in quantum field theory. It's seething with virtual particles, temporary fluctuations that pop into and out of existence. It has structure, properties, and follows specific laws. It exists within space-time and obeys quantum mechanics. This is not nothing. This is a particular state of something, a physical system with definite characteristics governed by mathematical laws. Calling it nothing is linguistic sleight of hand that obscures the conceptual issues involved. Actual nothing would be the absence of everything. No space, no time, no quantum fields, no laws of physics, no mathematical structures. From such absolute nothing, nothing can come because there's no mechanism, no process, no laws to drive any transition. The philosophical concept of nothing is not a physical state you can describe with equations. It's the absence of all physical states, all laws, all possibilities. And from this kind of nothing, something cannot arise because arising implies a process occurring in time according to rules. An absolute nothing has neither time nor rules. When cosmologists talk about the universe emerging from quantum vacuum fluctuations, they're talking about a transition within a pre-existing framework. The quantum vacuum already exists. The laws of quantum mechanics already hold. Space-time already provides the arena in which fluctuations occur. All of this already exists before the universe emerges. The universe doesn't come from nothing. It comes from quantum vacuum, plus the laws of quantum field theory, plus the mathematical framework that makes those laws meaningful. This shifts the origin question rather than answering it. Instead of asking, why is there a universe? We must ask, why is there a quantum vacuum obeying these specific laws? The mystery deepens rather than resolves. Some physicists acknowledge this explicitly. They'll say the quantum vacuum is nothing, only in the sense that it's the state of minimum energy, the baseline from which departures represent something. But they recognize it's not metaphysical nothing. Others are less careful. They slide between physical and philosophical definitions of nothing, using the ambiguity to make it seem like physics has solved a problem it hasn't actually addressed. The confusion extends to discussions of quantum fluctuations. Virtual particles in the vacuum are often described as coming from nothing, appearing spontaneously without cause. This violates energy conservation only temporarily. Borrowing energy from the vacuum and repaying it before the uncertainty principle would detect the violation. But this description is misleading. The vacuum isn't empty space waiting for particles to appear. It's a dynamic system where field excitations constantly occur. Virtual particles are mathematical artifacts representing these field dynamics, not literal particles popping out of nothingness. The language of particles appearing from nothing makes quantum field theory sound more mysterious than it is. It's actually a well-defined mathematical framework where the vacuum state has specific properties and fluctuations follow precise rules. Nothing about this is truly from nothing in the sense of violating causality or emerging without explanation. The universe from nothing narrative also ignores the problem of boundary conditions. Any cosmological model requires specifying initial conditions, the state from which evolution begins. Even models claiming to derive the universe from nothing must specify what that nothing is and what laws govern transitions from it. These specifications are not themselves explained. They're assumed as starting points for the calculation. Why these initial conditions rather than others? Why these laws rather than different ones? The model doesn't answer, can't answer, because it takes these as givens. So the universe doesn't come from nothing. It comes from initial conditions plus laws plus mathematical structure. All of these constitute something rather than nothing, and all of them require explanation just as much as the universe itself does. This doesn't mean cosmological models are wrong or useless. They're valuable for understanding how the universe evolved from early states to current conditions. They successfully describe cosmic history from fractions of a second after the Big Bang to the present, but they don't explain ultimate origins. They don't answer why there's something rather than nothing. They reframe the question in physical terms and then solve the reframed question, but the original question remains untouched. The myth of the universe from nothing persists because it's emotionally satisfying and conceptually clean. It suggests we've reached the end of questioning, that physics provides complete explanation. It avoids the uncomfortable admission that some questions might lie beyond science's scope. But honesty requires acknowledging limits. Science is extraordinarily powerful within its domain, explaining how things work, how they evolve, how they relate to each other. It's not equipped to answer why there's a domain at all, why the laws are what they are, why mathematical structures describe reality. These metaphysical questions aren't unimportant or meaningless, they're profound and inescapable. And the universe from nothing myth does a disservice by pretending they've been answered when they haven't. The truth is more complex and more humble. The universe came from prior conditions we don't fully understand, governed by laws we haven't explained, within a mathematical framework whose necessity remains mysterious. This is not nothing. This is a different kind of something that pushes the origin question back rather than resolving it. Look at what physicists call empty space, the quantum vacuum. You might imagine it as absolute nothingness, void waiting to be filled. But quantum field theory reveals something radically different. The vacuum is the most energetic thing in existence, a roiling sea of virtual particles and fluctuating fields, more something than the matter and energy filling the universe. This is not a metaphor. The quantum vacuum has measurable properties that affect real physics. It causes forces between metal plates in the Casimir effect. It contributes to the anomalous magnetic moment of electrons. It prevents electrons from falling into atomic nuclei. The vacuum is physically real and physically active. At any point in supposedly empty space, quantum fields pervade everything. These fields aren't things in space. They are space's fundamental contents. The electromagnetic field, electron field, quark fields, and dozens of others all exist simultaneously at every location. In their lowest energy state, the vacuum, these fields aren't inactive. Quantum uncertainty requires fluctuations. Field values oscillate around zero energy, never quite reaching it. These fluctuations manifest as virtual particles, temporary excitations that appear and disappear too quickly to be directly observed, but whose effects are measurable. The energy density of these vacuum fluctuations is staggeringly high. When you calculate it using quantum field theory, you get infinity, an obvious sign something is wrong with the calculation. Even when you apply cutoffs at the Planck scale, the vacuum energy density comes out enormous, vastly larger than any observed energy density in the universe. This is the cosmological constant problem, one of the worst quantitative discrepancies in physics. The vacuum should have huge energy density according to quantum field theory, but observations show it's nearly zero, smaller than theoretical predictions by more than 100 orders of magnitude. Something cancels almost all the vacuum energy, leaving only the tiny residual we observe as dark energy. We don't know what causes this cancellation or why it's not perfect. The near-zero vacuum energy seems like incredible fine-tuning, requiring contributions from different sources to cancel to astonishing precision. This mystery highlights how much we don't understand about the vacuum. It's not nothing. It's the most puzzling something in physics, a state whose energy we can't calculate correctly, despite having sophisticated theories. The vacuum also breaks symmetries. In particle physics, symmetries determine what's possible and what's forbidden. But some symmetries hold for the equations describing fields while being broken in the vacuum state itself. Electroweak symmetry is the classic example. The equations treat electromagnetic and weak nuclear forces symmetrically, as different aspects of the same fundamental force. But the vacuum doesn't respect this symmetry. The Higgs field has a non-zero value in the vacuum, breaking the symmetry and causing the forces to appear distinct. This spontaneous symmetry breaking is how particles acquire mass. The Higgs field fills the vacuum, and particles interact with it as they move through space. The interaction creates resistance we perceive as mass. Without the Higgs vacuum expectation value, most particles would be massless. So the vacuum determines fundamental properties of matter. It's not a passive backdrop, but an active participant in physics. The specific state the vacuum settles into affects what particles exist, what masses they have, and what forces govern their interactions. This raises profound questions. Why does the vacuum have the particular state it does? Other states are possible mathematically. The Higgs field could have different values, creating different physics. What selected the actual vacuum from the landscape of possible vacua? Inflation theory suggests our region of space underwent a phase transition, settling into one particular vacuum state among many possibilities. Other regions might have settled into different states with different physics. This would make our vacuum an environmental accident, one outcome among many in a vast multiverse. But this explanation requires pre-existing structure: the inflaton field that drives inflation, the landscape of vacuum states, the mechanism causing phase transitions. All of this exists before our vacuum forms. It's decidedly not nothing. The vacuum also has topology, a global structure beyond its local properties. In some theories, the vacuum can contain topological defects: cosmic strings, domain walls, monopoles. These are stable configurations that can't be smoothly transformed away. If our vacuum contains such defects, they'd be relics of the universe's formation, frozen in structures that reveal the vacuum's topological character. Searches for cosmic strings and monopoles haven't found them, but the absence of detection doesn't prove absence. They might be too rare or too faint to observe with current instruments. The vacuum might also be unstable. Current vacuum state could be metastable rather than the true ground state. If a lower energy vacuum state exists, our vacuum could eventually tunnel to it through quantum processes. This vacuum decay would be catastrophic. A bubble of true vacuum would nucleate somewhere, then expand at light speed, converting everything it encounters to the new vacuum state. Physics inside the bubble would be different, with different particle masses and different forces. Atoms would disintegrate, matter would reconfigure, and nothing would survive the transition. Calculations suggest our vacuum is stable, or at least has a lifetime exceeding the current age of the universe by many orders of magnitude. But certainty is impossible. The vacuum could decay tomorrow or never. We can't predict quantum tunneling events precisely. This possibility highlights how precarious our existence might be. We live not in solid, stable reality, but in a contingent state that happens to permit our existence. A different vacuum would have different physics, likely incompatible with life. The vacuum's properties also connect to the fundamental constants of nature. The masses of particles, the strengths of forces, the speed of light, all these emerge from how fields behave in the vacuum. Change the vacuum and you change the constants. This makes the constants seem less fundamental and more environmental. They're not written into the deepest laws of physics, but result from which vacuum state the universe happens to occupy. This deflates their apparent significance while making their values more mysterious. The quantum vacuum is also necessary for quantum field theory to work mathematically. You can't formulate the theory without defining a vacuum state relative to which excitations are measured. The vacuum is the reference point, the baseline from which all other states are defined. This makes the vacuum conceptually prior to particles and fields. In some sense, the vacuum is more fundamental than the things it contains. Particles are just excited states of vacuum, temporary departures from the baseline. Adding the vacuum is crucial for understanding physical reality at its deepest level. Yet the vacuum remains mysterious. We can calculate some of its properties and predict some of its effects, but we can't explain why it has the properties it does, or why this vacuum rather than another. The quantum vacuum demolishes any claim that the universe came from nothing. The vacuum is elaborately structured, rich with fields and fluctuations, governed by complex laws, and characterized by specific symmetries and energy states. If cosmological models start from the quantum vacuum, they're starting from something profound and puzzling that needs explanation as much as the universe itself does. They haven't eliminated the origin question. They've reformulated it in terms that are more precise but equally mysterious. Even if you grant that the universe could emerge from quantum vacuum fluctuations, you still face an insurmountable problem: the laws themselves. The laws of quantum mechanics, the equations of quantum field theory, the principles of relativity all of these had to exist and operate for the vacuum to fluctuate and the universe to emerge. Where did the laws come from? This question is often dismissed or ignored in popular cosmology, but it's fundamental. You can't have spontaneous creation without laws governing what's possible and probable. You can't have quantum fluctuations without quantum mechanics. You can't have space-time expansion without general relativity. The laws are something. They have structure, content, specificity. They constrain what can happen and determine how it happens. They're not nothing, and they don't come from nothing. Some physicists respond that the laws are just mathematical relationships inherent in nature, not things that need creating. Mathematics is eternal and necessary, they argue, so the laws derived from mathematics share that character. The universe follows mathematical laws because mathematical truth is inescapable. This view raises more questions than it answers. Why does the universe follow mathematical laws at all? Why these specific mathematical structures rather than others? Why is reality mathematical in the first place? The physicist Eugene Wigner called mathematics effectiveness in describing nature unreasonable. There's no obvious reason the universe should be deeply mathematical. It could have been chaotic, following no patterns, or it could have followed non-mathematical patterns. The fact that it's precisely describable by elegant equations is profoundly mysterious. Even if you accept that mathematics is somehow necessary or eternal, you haven't explained why physical reality instantiates these particular mathematical structures. Infinite mathematical structures exist abstractly. Only a tiny fraction of them correspond to actual physics. Why these and not others? The standard model of particle physics involves specific symmetry groups, specific field representations, specific coupling constants. Each choice could have been different mathematically. The fact that nature selects this particular combination requires explanation that saying it's just math doesn't provide. Then there's the problem of laws changing. In the early universe, physics was different. At extreme temperatures, forces unified. Symmetries that are broken now were unbroken then. Phase transitions altered the effective laws governing particle behavior. If laws can change, they're not eternal and necessary. They're contingent depending on conditions. This makes them seem more like states of a system than like eternal truths, more like patterns that emerge than like foundations that simply are. Inflation theory suggests laws might vary across space as well as time. Different regions could undergo different phase transitions, settling into different vacuum states with different effective laws. This makes laws environmental, variable features of different cosmic domains. But this requires meta-laws governing how laws change and vary. You need rules determining what phase transitions are possible, what vacuum states exist, what forces unify how. These meta-laws still require explanation. You can always push the question up one level, explaining laws in terms of deeper laws, explaining those in terms of even deeper laws. But infinite regress doesn't resolve the issue. At some point, you reach laws that are truly fundamental, not derived from anything else. These fundamental laws are brute facts, unexplained explainers, why they exist, why they're this way rather than another, why there are laws at all. These questions have no answers within physics because physics takes laws as given. Some theorists hope for a theory of everything that would unify all forces and explain all particles from one simple principle. String theory aspires to this, but even a theory of everything wouldn't explain why that theory, rather than another, why its mathematical structure is instantiated in reality. The mathematician Roger Penrose notes that even the most elegant unified theory would involve specific choices: the dimension of space-time, the gauge groups, the representations. Each choice could have been different. The theory might be simple, but its simplicity doesn't make it necessary or self-explanatory. There's also the puzzle of why laws are stable and universal. Physical laws appear to hold throughout the observable universe and to have held throughout accessible cosmic history. They don't vary from place to place or change randomly over time. This stability and universality isn't explained by the laws themselves. A law can't enforce its own universality. Something else ensures that the laws governing one region apply everywhere, that the constants measured here equal those measured in distant galaxies. In some cosmological models, this universality is an accident. Our observable universe happens to be causally connected, having originated from a small region where laws were uniform. Beyond our horizon, laws might differ, but this makes universality contingent rather than necessary, requiring explanation rather than being self-explanatory. The laws also appear fine-tuned for complexity and life. Change various constants slightly, and stars don't form. Chemistry becomes impossible, or the universe collapses before complexity can emerge. The range of parameters permitting complex structure seems narrow. This fine-tuning could be selection bias. We observe laws compatible with observers because incompatible laws don't produce observers. But this anthropic explanation requires many universes with varying laws, which requires meta-laws governing the multiverse. The fundamental question about laws' origins remains. Some philosophers argue that laws are descriptions rather than prescriptions. They don't make things happen. They describe what does happen. On this view, asking where laws came from is a category error, like asking where descriptions came from. But this seems to get causation backwards. Electrons repel each other because they have like charges, and electromagnetism makes like charges repel. The law describes this, but something makes it happen. That something, the electromagnetic field and its properties, needs explanation. Laws in physics aren't just correlations observed after the fact. They're principles that constrain what's possible and determine what's actual. They have explanatory and predictive power precisely because they capture something real about how nature works. The reality the laws capture requires explanation. Even if laws are just descriptions, what they describe, the patterns, regularities, mathematical structures pervading nature, still needs accounting for. There's also the question of laws' mathematical character. Physical laws are precise mathematical relationships expressible as equations. This mathematical precision seems arbitrary. Why should nature follow exact mathematical rules rather than approximate ones or none at all? The laws also involve specific mathematical structures, differential equations, gauge symmetries, Lie groups. These are sophisticated mathematical concepts that seem unnecessarily complex if laws are just arbitrary constraints on nature. Some have proposed that reality is fundamentally mathematical, that mathematical structures don't just describe nature, but are nature. This dissolves the question of why nature is mathematical, but raises the question of why mathematical structures have physical existence. The laws of physics stand as one of the deepest mysteries in cosmology. They are essential for universe formation, yet their origin remains completely unexplained. Cosmological models that claim to derive the universe from nothing invariably assume the laws as background framework. This assumption is never justified, rarely acknowledged, and fundamentally undermines the claim that something came from nothing. The laws are something complex and structured and specific. Their existence is at least as mysterious as the universe's existence. Any honest cosmology must admit this. The laws came from somewhere, or are somehow necessary, but we don't know which or why. This ignorance doesn't invalidate physics. The laws work regardless of whether we understand their origin, but it does invalidate claims that physics has explained cosmic origins completely. At best, physics has explained how the universe evolved given certain laws. It hasn't explained the laws themselves, And until it does, the origin question remains open. The universe is calibrated with extraordinary precision. Change the electron mass by a fraction of a percent, and chemistry breaks down. Adjust the strong nuclear force slightly, and stars can't form. Alter the cosmological constant minimally, and the universe either collapses immediately or expands so fast that structure never forms. This fine-tuning is not speculative. It's measured, quantified, undeniable. The parameters governing physics sit in narrow ranges that permit complex structure. Outside these ranges, the universe would be barren, incapable of producing galaxies, stars, planets, or life. Cosmologists have catalogued dozens of these fine-tunings. Each one seems coincidental, unexplained by deeper principles. Together, they create what's called the fine-tuning problem. Why are the constants precisely calibrated to permit our existence? Three explanations dominate discussion. First, necessity. Perhaps the constants couldn't have been different. Some unknown principle constrains them to their actual values. This would dissolve the mystery. The universe is this way because it must be this way. But we have no evidence for such principles. The constants appear independent in our theories. We can imagine changing them individually without affecting others. No known law requires their specific values. String theory was hoped to provide such constraints. Different string configurations might correspond to different constant values, with some fundamental principle selecting the configuration we observe. But string theory predicts a vast landscape of possible configurations, each giving different physics. Rather than solving fine-tuning, string theory makes it worse. Second explanation, multiverse. Perhaps countless universes exist with varying constants. We observe this particular universe because it's one of the rare ones where conditions permit observers. Universes with different constants exist but contain no one to observe them. This anthropic explanation shifts the question from why these constants to why does the multiverse exist? It trades one mystery for another while making the universe's fine-tuning less surprising. The multiverse explanation faces several problems. First, it's not directly testable. Other universes, if they exist, are causally disconnected from ours. We can't observe them or measure their properties. The multiverse remains speculation rather than established science. Second, it requires meta-laws governing the multiverse's structure. What determines how many universes exist? What range of constants they span? What mechanism generates them? These meta-laws need explanation as much as our universe's laws do. Third, it has a measure problem. If infinitely many universes exist, how do you calculate probabilities? Any outcome, no matter how unlikely, occurs infinitely often in an infinite multiverse. Making predictions requires specifying a measure for comparing infinities, and different measures give different predictions. Despite these problems, many cosmologists accept some form of multiverse because fine-tuning seems so improbable otherwise. They view the anthropic principle that we observe conditions compatible with observation as genuinely explanatory. The third explanation is design. Intelligence deliberately set the constants to permit life. This is the only explanation that makes fine-tuning unsurprising. If the universe was designed for life, finding it calibrated for life is exactly what you'd expect. Most scientists reject design on philosophical grounds. It invokes agency beyond physics, something science traditionally excludes from explanations. It also raises questions about the designer's nature and origin that seem to push the explanation back without resolving it. But design has an advantage. It makes fine-tuning probable rather than improbable. In a designed universe, you'd expect calibration for purpose. In a random universe, calibration is inexplicable coincidence. This is why the fine-tuning argument has force, despite resistance to its implications. None of these explanations is fully satisfactory. Necessity lacks evidence. Multiverse is untestable and requires problematic meta-assumptions. design steps outside science's methodological framework, we're stuck with a mystery that none of our standard approaches resolves cleanly. The fine-tuning problem undermines claims that the universe came from nothing. If the universe randomly fluctuated into existence, we'd expect random constants uniformly distributed across possible values. Instead, we find constants precisely calibrated in narrow ranges. This calibration requires explanation. Random origin can't explain it because randomness predicts typical values, not rare fine-tuned ones. You need either a selection, mechanism, multiverse, a constraining principle, necessity, or intentional calibration, design. All three involve something beyond the bare existence of the universe. The multiverse is something. Constraining principles are something. A designer is something. You can't explain fine-tuning from nothing. You need additional structure. Some cosmologists try minimizing fine-tuning significance. They argue that we don't know the full range of possible physics. Maybe different constant combinations produce complexity through mechanisms we haven't discovered. Maybe life-permitting ranges are wider than we think. These arguments are possible but speculative. We can only work with physics we know, and known physics shows narrow habitability ranges. Imagining unknown physics that changes this is just that, imagination without empirical support. Others argue that fine-tuning is observer selection bias. Of course, we observe values compatible with observers. Incompatible values don't produce observers to be surprised. On this view, fine-tuning is no more remarkable than finding yourself born in a habitable environment rather than in space. But this reasoning has limits. If only one universe exists and constants were set randomly, finding ourselves in a fine-tuned universe would be astonishingly unlikely. You can't fully dissolve the improbability through anthropic reasoning without multiple universes to select from. The fine-tuning problem also extends to initial conditions. The universe began in a state of extraordinarily low entropy, a vastly improbable configuration if chosen randomly from all possible states. This low entropy was essential for structure formation. Without it, the universe would have been born in maximum entropy, unable to evolve complexity. Why the low entropy initial state? Inflation provides partial explanation, saying the pre-inflation universe needed only a tiny patch of low entropy that inflated enormously. But this pushes the question to inflation's initial conditions, which themselves seem fine-tuned. The cosmological constant presents especially stark fine-tuning. Quantum field theory predicts vacuum energy should be enormous. Instead, it's tiny, but non-zero, precisely the value needed for structure formation. Too large, and expansion would have prevented galaxy formation. Too small, and, well, it's hard to see why it's not zero if it's that small. The cosmological constant appears calibrated to more than 100 decimal places. This is the most precise fine-tuning in all of physics. No known principle explains it. It stands as stark evidence that something beyond random chance determines the universe's parameters. Some cosmologists hope that a theory of everything will explain fine-tuning by deriving all constants from one fundamental principle. The constants would turn out to be necessary consequences of deeper mathematics, removing the appearance of calibration. But even elegant mathematical theories involve choices. String theory involves the dimension of space, the compactification scheme, the vacuum state. Loop quantum gravity involves discrete structures and parameters. Any theory makes assumptions and includes free parameters requiring explanation. The fine-tuning problem reveals that the universe is not a random accident. Its parameters are set with precision incompatible with chance. Whether this precision reflects necessity, selection from multiple universes, or intentional design, it indicates the universe's origin involves more than spontaneous emergence from nothing. The precision is something that needs explaining. The narrow ranges are something beyond bare existence, fine-tuning points toward prior structure, prior intelligence, or prior constraints that shaped the universe's properties. None of this is nothing. All of it is something that undermines the narrative of spontaneous creation from void. The universe shows every sign of arising from something, not nothing, something that set its parameters with extraordinary precision for reasons we don't fully understand. The Big Bang theory says time began at the initial singularity. Before the Big Bang, there was no time, so asking what came before is meaningless. This seems to resolve origin questions cleanly. Without before, there's no prior cause to explain. But this resolution creates more problems than it solves. If time began, what caused it to begin? Causation is a temporal concept. Causes precede effects in time. Without time, there's no precedence, no before in which a cause could operate. You're left with time beginning uncaused, which seems to violate the principle that everything has a cause. Or you must redefine causation in non-temporal terms, which nobody has done satisfactorily. The beginning of time creates a conceptual paradox that dissolves neither cleanly nor easily. Some argue that time didn't begin absolutely, but emerged from something more fundamental. Pre-Big Bang cosmologies propose various scenarios: eternal inflation, cyclic universes, quantum gravity foam, higher dimensional brains. In these models, time as we know it began at the Big Bang, but some more fundamental temporal parameter existed before. This avoids the paradox of absolute temporal beginning, while raising questions about the pre-Big Bang state and what allowed transition to our current universe. Eternal inflation is the most popular pre-Big Bang scenario. It proposes that inflation is eternal into the past and future, with pocket universes like ours occasionally nucleating from the inflating background. Our Big Bang was one such nucleation event, not an absolute beginning. This elegant picture has problems. The inflating background still requires explanation. It's not nothing but a specific quantum state with specific properties, and mathematical theorems by Arvind Borda, Alan Guth, and Alexander Vilenkin suggest that eternal inflation cannot be infinitely past eternal. It must have a beginning too. If eternal inflation began, you're back to the original problem. What caused that beginning? The issue is pushed back but not eliminated. Every cosmological scenario that avoids absolute temporal beginning simply shifts where the beginning occurs. Cyclic cosmologies propose that universes repeatedly expand, contract and bounce with no absolute beginning or end. Our Big Bang was a bounce from a previous contracting phase, which itself followed an earlier expansion. This sounds appealing. No beginning, no end, just eternal cycles. But cycles face severe difficulties. Entropy increases in each cycle unless something resets it. If entropy builds over cycles, you can trace backward to find when it was zero, identifying an effective beginning despite formal eternality. Attempts to reset entropy in each bounce require specific physics that seems fine-tuned for that purpose. The bounce conditions need precise calibration to avoid singularities or to allow the universe to re-expand. You trade the problem of initial conditions for the problem of bounce conditions. Quantum cosmology takes a different approach, describing the universe's origin using quantum mechanics. The Wheeler-DeWitt equation treats the entire universe as a quantum system with a wave function. The universe could tunnel from nothing into existence, like a particle tunneling through a barrier. But nothing in quantum cosmology isn't philosophical nothing. It's a particular quantum state, the no spacetime state. This state still exists within the mathematical framework of quantum mechanics. The laws, the wave function, the quantum operators all exist and operate even when classical spacetime doesn't. So, quantum creation isn't creation from absolute nothing, but from a peculiar quantum state characterized by absence of classical spacetime. This state is something rather than nothing. It has structure, obeys laws, and contains the potentiality for space-time emergence. The Hartle-Hawking no-boundary proposal offers another quantum origin scenario. It suggests the universe is finite in space-time, but has no boundary or beginning, similar to how Earth's surface is finite, but has no edge. Time becomes space-like in the early universe, making the question of beginning ill-posed. This mathematically elegant proposal avoids the beginning problem, but requires imaginary timing calculations, which may or may not correspond to physical reality. It also requires specific choices of wave function and measure that determine probabilities, choices that themselves require justification. All these scenarios, eternal inflation, cyclic cosmology, quantum creation, no boundary proposal, avoid absolute beginning of everything, but don't avoid beginning of something. They all involve pre-existing mathematical structures, physical laws, quantum states, or background frameworks within which the universe emerges. The time-beginning paradox illuminates a deeper issue: causation's nature. We're accustomed to causes preceding effects temporally, but if time itself has a beginning or emerges, temporal precedents can't explain that beginning or emergence. Some philosophers propose atemporal causation, logical or ontological dependence that doesn't require temporal precedence. The universe might be caused in the sense of depending on something else for its existence, without that something being temporally prior. This kind of causation is abstract and difficult to grasp intuitively. We have no clear examples of atemporal causes in ordinary experience. It's a conceptual tool introduced to solve the beginning problem, not derived from observation or established physics. Even if a temporal causation makes sense, it requires a cause, something on which the universe depends, even if not temporally prior. That something is not nothing. It's a ground of being, a foundation, a source from which the universe derives, even if the derivation isn't temporal. Some cosmologists embrace a more radical view. Time might be emergent and not fundamental. At the deepest level, the universe might be timeless, with time arising only in particular contexts or approximations. Carlo Rovelli and others working on quantum gravity suggest that time is not a fundamental feature of reality, but emerges from more basic, timeless quantum interactions. If true, the universe's beginning is an artifact of our time-based perspective, not a fundamental feature of reality. But timeless descriptions still involve structure, timeless quantum states, interaction rules, mathematical frameworks. These aren't nothing. But timeless descriptions still involve structure, timeless quantum states, interaction rules, mathematical frameworks. These aren't nothing. They're richly defined systems with constraints, symmetries, and rules governing what can exist and how it can relate. A timeless universe is not an empty void. It's a static totality described by complex equations that encode potential change, even if change itself is not fundamental. If time is emergent, then something deeper gives rise to it. Emergence doesn't happen from absence. It requires an underlying substrate with properties capable of producing the emergent feature. Temperature emerges from molecular motion. Pressure emerges from particle collisions. Meaning emerges from neural activity. In every case, emergence presupposes a structured foundation. So if time emerges, what does it emerge from? A timeless quantum reality? A static configuration space? A mathematical object? Whatever the answer, it is not nothing. It is something capable of giving rise to temporal experience. And once again, the origin question is not solved, only relocated. The deeper problem is that beginning itself may be the wrong concept. We imagine beginnings as events that happen at some first moment. But if time is part of the system that began, then no first moment exists within the system. The beginning is not a point in time, it is a boundary of explanation. This boundary is where physics grows quiet. Physics is extraordinarily good at describing relationships within time, how states evolve, how causes produce effects, how systems change. But when asked to explain the existence of time itself, physics has no established framework. Its equations presuppose time or replace it with something mathematically equivalent. They don't generate it from absence. This is why cosmological explanations often rely on metaphor. We hear phrases like, the universe popped into existence, time turned on, or the universe booted up. These metaphors are useful for communication, but they conceal conceptual gaps. They describe something happening without a when. Nothing happens without time. Events require a temporal dimension. Change requires duration. Becoming requires before and after. If time itself emerges, that emergence cannot be an event in time. It must be something fundamentally different. And that difference matters, because the moment you abandon temporal causation, you haven't eliminated causation. You've changed its form. You're now talking about dependence, grounding, or necessity. The universe depends on something more fundamental than time, something that explains why temporal reality exists at all. That something might be mathematical. It might be physical in a sense we don't yet understand. It might be metaphysical. But it is not nothing. Some physicists suggest the universe is self-contained, that it simply exists without explanation. There is no why, only is. Time exists because it exists. The universe exists because it exists. Asking why is meaningless. This position is logically possible, but it is not explanatory. It's a refusal to explain rather than an explanation. And it's worth noticing that this move is rarely accepted elsewhere. We don't accept it just exists for complex systems when other explanations are available. We don't say a watch exists without cause. We don't say a computer program just exists without explanation. The more structured something is, the more explanation it seems to demand. The universe is the most structured thing imaginable. It contains laws, constants, symmetries, asymmetries, initial conditions, and a deep mathematical order. To say this entire structure simply exists without reason is not scientific humility, it's philosophical surrender. Even worse, the "it just exists" response quietly abandons the original claim. If the universe just exists, then it didn't come from nothing. It came from itself, or from necessity, or from brute fact. In any case, not from nothing. The time-beginning paradox reveals something crucial. The universe cannot be explained purely in terms of temporal processes. Any explanation must ultimately be non-temporal, and non-temporal explanations require foundations more fundamental than physical events. That pushes us into uncomfortable territory, because once you admit that the universe depends on something beyond time, you are no longer doing standard cosmology. You are doing metaphysics, whether you like it or not. And this is exactly where the universe from nothing story breaks down. It promises an explanation that avoids metaphysics, avoids first causes, avoids ultimate questions. But the moment you examine time closely, what it is, how it began, whether it's fundamental, you are forced back into those questions. Time either began or it didn't. If it began, something non-temporal explains its beginning. If it didn't, something eternal explains its existence. Either way, the universe is grounded in something beyond itself, and that something is not nothing. The paradox of time is not a flaw in cosmology, it's a signal, a signpost indicating that the deepest layer of reality is not described by clocks, durations, or temporal sequences. The ultimate explanation of the universe will not be a story that starts with "and then." It will be a story that starts with because something exists rather than nothing, because structure exists rather than chaos, because laws exist rather than randomness, because time exists rather than timelessness. And until those becauses are addressed, Any claim that the universe came from nothing remains incomplete at best and misleading at worst. The Big Bang marks the beginning of our observable cosmic history. It does not mark the origin of existence itself. It is a boundary of knowledge, not a point of absolute creation. And mistaking that boundary for nothingness is one of the most persistent illusions in modern science. At this point, the phrase nothing itself deserves scrutiny, not because it's poetic or provocative, but because it may be the most abused word in all of cosmology. We use it casually. We say a room is empty. We say space is empty. We say before the universe there was nothing. But in physics and in philosophy, these statements quietly collapse under inspection. Because true nothingness, absolute nothingness, does not exist in any theory we have ever constructed. Not in physics, not in mathematics, not even in logic. What we call nothing is always something stripped down, minimized, abstracted, but never truly absent. Empty space is not empty. We've already seen that. It's filled with quantum fields, vacuum energy, structure, and potential. Even when you remove all particles, space itself remains, with geometry, dimensionality, and measurable effects. Remove space, and you still have laws, equations that describe what space would do if it existed. Remove laws, and you still have mathematics, the logical structures that define possibility and impossibility. Remove mathematics, and you still have logic, the framework that allows removal to be intelligible in the first place. At no point do you arrive at nothing, because nothing is not a thing you can arrive at. It is not a state. It is not a condition. It is not a background. It is the complete absence of all being, all structure, all possibility, including the possibility of absence. And that kind of nothingness cannot produce anything. This isn't a religious claim. It's not a metaphysical preference. It's a logical constraint. From nothing, nothing comes, not because of tradition or doctrine, but because coming requires something to come from and something to operate. Creation is an action. Actions require actors or mechanisms or rules. None of these exist in nothingness, which means any theory that describes the universe as emerging from nothing is either using the word incorrectly or smuggling something in through the back door, and they almost always are. When physicists say nothing, they often mean no classical matter, or no space-time as we know it, or lowest energy state allowed by the theory. These are technical definitions, not existential ones. But popular science collapses these distinctions. The audience hears nothing and imagines absence. The theory means something minimal but structured. The result is confusion masquerading as insight. This is why the phrase universe from nothing is so effective and so misleading. It exploits a gap between technical language and intuitive meaning. In philosophy, nothingness is not emptiness, it is non-being. It has no properties, it has no laws, it has no tendencies, it has no probabilities. It cannot fluctuate, because fluctuation is change, and change requires time, structure, and rules. Quantum fluctuations do not occur in nothing. They occur in quantum fields governed by equations defined over mathematical spaces. Calling that nothing is like calling the ocean empty because there are no boats on it. Once this is understood, a startling realization emerges. Every cosmological origin theory begins with something, a vacuum, a field, a law, a wave function, a mathematical structure, a timeless quantum state. The disagreement is not whether something existed before the universe. The disagreement is what kind of something it was. And that shifts the entire debate. The question is no longer, did the universe come from nothing? The question becomes, what is the most fundamental something? Is it physical? Is it mathematical? Is it abstract? Is it necessary? Is it contingent? These are not scientific questions in the narrow sense. They are foundational questions. Questions about the nature of reality itself. Some physicists embrace mathematical realism, the idea that mathematical structures exist independently, and that physical reality is one such structure. On this view, the universe exists because the mathematical structure corresponding to it exists. But this doesn't eliminate the mystery. It relocates it. Why that structure? Why this one rather than another? Why is it instantiated as experienced reality rather than remaining abstract? Others argue that existence itself is necessary, that something must exist rather than nothing, and that the universe is that something. Nothingness, on this view, is impossible. Reality exists because non-existence cannot. This position has intuitive appeal, but it raises questions. If existence is necessary, why does it take this particular form? Why laws instead of chaos? Why stable structures instead of incoherent flux? Necessity alone does not explain specificity. Some attempt to dissolve the issue by claiming that nothing is unstable, that nothingness naturally gives rise to something. But this idea is incoherent. Instability is a property. It requires dynamics. It requires potential. It requires laws governing transitions. Nothingness has none of these. If nothing were unstable, it wouldn't be nothing. The more carefully you examine the concept, the clearer it becomes. Nothingness is not a physical possibility. It is an abstract negation, a linguistic placeholder for absence, not a state reality can occupy. Reality either exists or it doesn't. And if it doesn't, there is no it to transition. This is why philosophers from Parmenides to Heidegger have argued that nothingness is not something from which being can arise. Being cannot emerge from non-being. Any origin story that suggests otherwise quietly replaces nothingness with a hidden substrate. And modern cosmology is no exception. The difference is that the substrate is now mathematical and quantum rather than mythological. But it is still a substrate, still structured, still governed by rules, still something. Once you see this, the original claim collapses. The universe did not come from nothing. It came from whatever reality is when stripped of space, time, matter, and energy, but not stripped of structure. And that reality is not empty. It is foundational. This realization doesn't diminish science. It clarifies its scope. Science excels at describing how one state evolves into another. It is unmatched in tracing causal chains, modeling dynamics, predicting outcomes, but it does not and cannot explain why there is a chain at all. Nothingness is not a scientific hypothesis. It is the absence of hypotheses. And because of that, it cannot do explanatory work. The idea that science has shown how something came from nothing is not a discovery. It is a rhetorical shortcut, one that trades precision for provocation. The truth is more subtle, more unsettling, and more profound. Reality has no known origin in nothingness. Every explanation rests on an underlying is, and the moment you admit that, you are no longer asking about physics alone. You're asking about existence itself. In the next section, we confront the final consequence of this realization, what it means for the claim that science has eliminated the need for deeper explanations, and why the universe's existence may be the ultimate unanswered question rather than a solved one. There is a quiet assumption woven through modern culture that science has replaced mystery with mechanism. That where once we asked why, we now ask only how. That the universe, once terrifying and profound, has been reduced to equations that leave no remainder. This assumption is wrong. Science did not end the mystery of existence. It refined it. The more we learn about the universe, the more precise our questions become. And the more obvious it is that some of them remain unanswered, not because we lack data, but because they lie outside the domain of empirical methods altogether. Science explains how the universe behaves given certain conditions. It does not explain why those conditions exist in the first place. This distinction is often blurred, sometimes intentionally. When cosmologists describe the early universe, they talk about energy densities, symmetry breaking, inflationary fields, quantum states. These descriptions are powerful, They allow us to rewind cosmic history with astonishing accuracy. They let us model the universe back to fractions of a second after the Big Bang. But notice what is missing. At no point does the explanation begin from true absence. At no point does science derive existence from non-existence. It always starts with a framework already in place. And that framework, laws, fields, mathematical structures, is not explained by the theory. It is assumed. This is not a failure of science. It is a boundary. Science is a method for studying relationships between phenomena. It requires phenomena to exist. It cannot, by its own nature, explain why there is something rather than nothing, because that question is not about relationships within reality, but about the existence of reality itself. Yet popular narratives often overstep this boundary. They claim that physics has shown the universe requires no explanation beyond itself. That asking why does anything exist is an outdated, meaningless, or even unscientific question. But dismissing a question does not answer it. It simply changes the subject. The irony is that the deeper physics goes, the more it relies on assumptions that look increasingly philosophical. Concepts like law and state, possibility, necessity, and ground are not empirical measurements. They are conceptual foundations. Even the idea that the universe can be described mathematically is not something science explains. It is something science presupposes. Why mathematics works at all remains unexplained. Why reality obeys stable laws remains unexplained. Why those laws permit complexity remains unexplained. Why existence exists remains unexplained. These are not gaps waiting for future experiments. They are questions of a different kind. Some scientists acknowledge this openly, others resist it, fearing that admitting limits undermines science's authority. But recognizing limits is not weakness. It is intellectual honesty. The problem arises when scientific success in one domain is mistaken for total explanatory power. Just because science can explain stellar evolution does not mean it explains why stars exist at all. Just because it can model cosmic inflation does not mean it explains why there is a cosmos to inflate. When science is stretched beyond its proper scope, it turns into ideology. And the universe from nothing narrative is exactly that, an ideological claim disguised as a scientific conclusion. It is not derived from equations. It is not demanded by data. It is a philosophical interpretation layered onto physical models. And it is optional. You can accept all of modern cosmology, Big Bang, inflation, quantum fields, particle physics, without believing the universe came from nothing. In fact, once you understand those theories correctly, it becomes hard to see how you could believe that. Every model assumes existence. Every explanation presupposes structure. Every calculation relies on laws that are not themselves calculated. The universe, as described by science, is not a brute accident popping out of void. It is an ordered system emerging from deeper order. That deeper order may be physical, mathematical, or something we do not yet have language for. But it exists, and its existence is unexplained. This realization doesn't undermine science, it restores its humility. Science is not a replacement for metaphysics. It is one branch of human understanding, extraordinarily powerful within its limits, but not limitless. When those limits are denied, science becomes dogma rather than inquiry. The true lesson of modern cosmology is not that mystery has been eliminated. It is that mystery has been pushed deeper. We now know far more about the universe than any generation before us. We know its age, its composition, its large-scale structure. We know how stars form, how galaxies evolve, how atoms bind. But the most fundamental question remains untouched. Why is there something rather than nothing? Not because we haven't tried hard enough, but because the question points beyond mechanisms and measurements. It points to the ground of being itself. Some find this uncomfortable. They prefer a closed system, a universe that explains itself and needs nothing beyond physics. But closure is not the same as explanation. Saying that's just how it is not an answer. It is an admission of ignorance, framed as confidence. And there is nothing wrong with admitting ignorance. What is wrong is pretending that ignorance has been eliminated when it has not. The universe is intelligible, ordered, lawful. That is already astonishing. That such a universe exists at all is even more so. Science tells us how it behaves. It does not tell us why it exists. And any claim that it does is not science speaking, but philosophy wearing a lab coat. In the final section, we confront the unavoidable conclusion of everything we've uncovered. What the universe's refusal to emerge from nothing actually tells us about reality, explanation, and the limits of human knowledge. After everything we've stripped away, matter, energy, space, time, laws, even causation itself, one question remains, untouched and unavoidable. Why does anything exist at all? This question survives every scientific advance because it does not live inside the universe. It stands outside it, pointing not to how reality behaves, but to the fact that reality is there to behave in the first place. And that is the final truth hidden beneath the phrase, the universe came from nothing. The universe did not come from nothing, because nothing is not a place, nothing is not a state, nothing is not a cause, and nothing does not do anything. What exists because something is fundamentally real. Something is primary, something is unavoidable. Whether you call that something a quantum foundation, a mathematical structure, a necessary reality, a ground of being, or something for which we do not yet have language, it is not nothing, and the universe depends on it. This dependence is not temporal, it is not before, it is not an event, it is deeper than time. It is explanatory rather than chronological. The universe exists because, not after. This distinction matters more than it first appears, because once you accept it, the popular story collapses. The story that science has shown existence to be accidental. The story that reality is a meaningless fluctuation. The story that there is no deeper explanation to be sought. Those stories are not scientific conclusions. They are philosophical preferences. Science itself tells a different story, quietly, indirectly, but unmistakably. A story of order, a story of structure, a story of laws that do not explain themselves. A story of precision that defies randomness. A story of existence that refuses to dissolve into nothingness. The deeper we look, the less plausible nothingness becomes. The universe does not look like a mistake. It does not look like a glitch. It does not look like a temporary violation of absence. It looks grounded. Grounded in something that does not come and go, something that does not fluctuate, something that does not depend on time to exist. And this is where many people instinctively turn away, because this is where explanations stop being comfortable. If the universe did not come from nothing, then reality is not self-explanatory. If reality is not self-explanatory, then there is something more fundamental than the physical universe. And that realization destabilizes easy assumptions. It does not force a particular conclusion. It does not tell you what the foundation is, but it tells you what it cannot be. It cannot be nothing. It cannot be random. It cannot be unexplained chance emerging from absence. Those ideas dissolve under scrutiny. What remains is mystery, but not ignorance. A structured mystery, a bounded mystery, a mystery surrounded by clarity about what explanations fail. And that matters, because dismissing the question does not make it disappear. It only ensures that it will be answered badly, through slogans, oversimplifications, or ideology. The honest position is harder. It is to admit that science has taken us astonishingly far, but not all the way. That physics explains evolution, not existence. That cosmology explains history, not origin. That nothing has never been an answer, only a word used to hide unanswered questions. This is not a failure of knowledge. It is a recognition of depth. The universe is not shallow enough to be explained away. And perhaps that is the most important insight of all. Not that we lack explanations, but that reality itself may be the kind of thing that cannot be explained away completely, only understood more deeply. The universe did not come from nothing. It came from whatever reality is when stripped to its most fundamental form. And that reality, whatever it is, demands our humility, our curiosity, and our honesty. Because the question that started everything, why is there something rather than nothing, has not been answered. It has been clarified, and it is still waiting.